Okay, welcome to the lecture for Monday, March 24th. We will be talking about waves on a string, first of all. So waves on a string. So recall, we had several demos last time. I don't have the demos here in my office, but you probably remember some of these traveling wave demos we did. So the traveling wave, okay, if you forget what a traveling wave is, I have a cheap imitation of a traveling wave here. Sorry for the cheap theatrics here, but it's just a wave that moves along like this, okay? It retains its shape and just moves along like that. And we'll be talking about a sine wave. So a sine wave that will have this form. So I'll write it as y is equal to a times the sine of kx minus omega t. Okay, the a is what we've been calling the amplitude. Same thing as before. K is the wave number. Okay, and K also happens to be equal to 2 pi divided by the wavelength. This guy is the wavelength. And omega is what we call the angular frequency. And I can make a little bit of an analogy here. It's also equal to 2 pi divided by the period, where t is the period. Okay, now if I'm calculating the wave speed, and we did this last time, so the wave speed is v, and that's equal to you can write it several different ways. You can think of it as lambda over the period, the wavelength over the period. If you're trying to keep this in your head, the easiest way to think about this is the wave speed has units of meters per second, so lambda over t has the right units. That's how I actually remember this. Lambda has units of meters, t has units of seconds, so lambda over t is the wave speed. You can do it a different way. You know that angular frequency has units of radians per second, or just inverse seconds, and k, the wave number, has units of inverse meters. So if I want to get something that's a wave speed, I take the thing that's inverse seconds divided by the thing with inverse meters. So then the meters goes upstairs, the seconds goes downstairs, and that's another way to write the wave speed. It's omega over k. Okay. Now, what determines the speed of waves on a string? So we're talking about waves on a string, a little traveling wave. Think about our little traveling wave moving, let's say, in this direction. So you should remember from last time that when I have kx minus omega, sine of kx minus omega, like this with the minus sign, it actually moves in the positive x direction. The wave actually moves the way I showed you just before. When it's moving in this direction, the positive x direction. If I had kx plus omega t, it would actually move in the opposite direction, that way. But the speed of the wave is determined by the tension in the string. Okay, just think of a string like a guitar string, piano string, violin string, something like that. And there's some tension in the string. There's also some mass per unit length of the string. Both of those things determine how fast the wave speed is. And the formula, we won't go through the derivation of the formula for this. It's actually quite complicated, that's why we're not doing it. But I'll give you the formula. So we will let the mass per unit length of the string be, mass per unit length is going to be mu. Okay, and the tension, the reason why it's mu, by the way, is it starts with the letter m. It's supposed to remind you of the word mass. And a cheap trick that physicists like to use is to use Greek letters for things per unit length or per unit volume. Now the tension in the string, we'll write that as, we can write it as capital T, but sometimes you might, we've used capital T for period, so that's no good. So let's actually write FT so that it's clear that's tension, it's not period or something, okay? So if we know the tension in the string and we know the mass per unit length of string, then the wave speed V, the formula for the wave speed is it's the square root of Ft divided by mu. That's the formula. We're not deriving it, but we can check. Well, you can check it. You can check that it gives you the correct units. The tension is actually units of newtons, which happens to be kilograms meters per second squared. If you divide it by the mass per unit length, which is kilograms per meter, this will end up, this ratio will end up having the kilograms drop out, and you'll end up with meters squared per second squared. If you take the square root of that, the units will work out. You get a speed which has units of meters per second. If you don't believe what I just said, just try it out yourself. Now, the next thing I'd like to talk about is this superposition principle, which is actually really very, very simple. It's kind of a big word for something very simple. Superposition principle. And it's just the statement that you can add waves together. Okay? When two waves cross, the result is the sum of the two waves. Okay, so let me try to show you. So let's not make full sine waves for the waves, but let's just make two little bumps. Okay, so let's suppose I have a little bump here, and let's suppose it's moving in this direction, and then I have a, let's say, a little bigger bump so you can tell which one is which, and it's moving in this direction. Okay, so that's one snapshot. Let's suppose this is how it starts off. Now a little time later, this guy over here will have moved, so now it's over here. Okay, and this guy has moved as well, so now it's over here. Okay, so they're still moving towards each other. Okay. And then eventually they'll just pass through each other. So this guy is actually now over here. So the big bump here. And the small bump will be over here. So this guy's passed through, this guy has passed through as well. So they just pass through each other, and at any given time, it's just the sum of the two individual waves that gives you the entire disturbance. Okay, now that we know that you can add waves together, it's useful to talk about this concept of interference. And the interference will be something we'll be talking about quite a bit throughout the rest of this course. So, so we'll talk about interference. Okay. And the first type of interference we'll talk about is constructive interference. Constructive or in-phase interference. All right. Now, constructive or in-phase interference is when things go up and down together. You have two waves going up and down together, and you just add them together, and you get double the amplitude. It's really quite simple. So let me show you. Right. What's complicated about drawing these waves is you can either draw them as a function of time, or you can draw them as a function of space. So let me just show a snapshot. At time t equals to 0. Okay, so I'm drawing it versus position. And suppose I have one wave that does this. Okay, right. Okay, so this is your amplitude, that's how high it gets, and negative A is how low it gets. And this is position of the wave, so let's suppose it's x versus, so I'll think of it as a wave that goes up and down in the y direction. It's a transverse wave. Okay, now let's suppose I add another wave just like it. That goes between A and minus A, very simple. Does the same thing, and it's all lined up, so this point here will line up there, this point here will line up there, this point here will line up there. Okay, so we have this. Okay, if I add those together, well, it's just the same wave, so you add them together, you just get double what I had, so then the disturbance will be twice as big in amplitude. Okay, we'll have, this is A, so this is 2A. Here, way down here is minus 2A. So you have the big old wave with double the amplitude. Okay, that's constructive. They add together, they're working in cooperation, so that's why we call it constructive. If I want to write this in equations, it's pretty straightforward. Okay, so I have y, the disturbance, will be a sine kx minus omega t, so I'll put in the time dependence now. And then let's suppose I have another wave that's just like it. So what we say, because they go up and down exactly in the same way, because they're actually exactly the same function, we say these guys are in phase. They are in phase. You've probably heard that term before. They're doing the same thing. Okay, so if I have this, then it's not so hard to see that this, I just add them together and get 2a sine kx minus omega t. Okay, so that is constructive interference when you have this adding together of the waves. Now, the next case I want to consider is what's called destructive interference. Okay, so destructive interference. So destructive, or let's call it 180 degrees out of phase interference. And in this case, we have a plot like this. So I have to draw this again. I have A minus A, and I have my wave goes up and down like that. Okay, and this is X and this is Y, so again this is a snapshot at time t equals to 0. And now I will have another wave. Okay. Here. And what I'll do with this wave is I will actually just shift it over. I would just shift it over like this, okay, by 180 degrees. So that this point will actually go to here. So the minimum will be here. Alright. Well, let me try to line things up. So I've shifted it by 180 degrees. Alright. So now I will have something like this. Right. Now, shifting by 180 degrees, that actually just is the same thing as taking the negative of the function. So that's a simple way of understanding what will happen now if I add these together. If I add them together, I will get, well, if they're negatives of each other, y here, then I just get a big fat nothing. I get 0. Okay, so this is what's called destructive or 180 degree out of phase interference, because they're 180 degrees shifted from each other, or half a cycle shifted from each other. Now, if I want to think of this in equations, I can think of it this way. So I have y for one wave is a sine kx minus omega t. The other one will be a sine kx minus omega t, but I'm shifting it by 180 degrees. So let's just stick in a pi, which is the same thing as 180 degrees. So I like to think in terms of radians here. Okay, but if I add 180 degrees to the angle, then the sign will just flip its sign, right? So it will just get a minus sign. So this will give me a sine kx minus omega t, and minus sine of kx minus omega t. Right? Okay, so that will give me just plain old 0. Now in the notes, I actually go through the general case where you put in a general angle phi, and what you get in that case would be, you can sort of interpolate between 180 degrees out of phase, destructive, and constructive. But I'm not sure that we actually need to do that. If we need this later, I will derive the general formula for general phi, but let's skip that in the notes, and I'll do it if that's something we'll need, but usually that's not something we'll be doing in the course. Okay, now if you have any questions up to this point, please send me an email. Okay. Otherwise, let's go on to talk about reflection. And I'll have a demo for this when I'm back in class on Wednesday. Okay, so let's think about reflection. So we have, okay, so think about this. We have a wall here, okay? And let's say we have a string that's tied to a wall, but there's a pulse being sent. You flick you flick a piece of the string so that it has a little bump and it travels. So we have an incident pulse. But the string is attached to a wall. It's tied to a wall, so that it's not going to move here. It's fixed here, fixed end. Alright, let's just think a little bit qualitatively about what's going to happen. So this pulse will keep going, nothing exciting will happen until it gets close to this wall. Alright, now when it's really close to this wall, as it gets right up against the wall, notice how as this pulse comes closer, because this point is fixed here, it's not moving, the string will have this funny shape where it bends up like this, straight up like that. Now, let's think a little bit about the forces that are acting here. So we know that the string basically just pulls on the end with some tension, okay? It pulls up like this. So the string is pulling the wall up like this, okay? Pulling up, that's the way the string will be pulling. But then the wall will be actually pulling the string down like that, okay? Because the string is pulling the wall up, the wall is, by Newton's third law, is pulling the string down. So because there's a force pulling, the wall is pulling the string down, it will actually flip this guy over. And so it was coming in upright like this, but you'll find that what happens is when it leaves, it will actually flip over before it leaves, okay? So the reflected pulse, this is what's called reflection. The reflected pulse, when you have a string that's tied on one end, the reflected pulse will be upside down. This is just a concept thing, but sometimes this is kind of useful to know. If you have never seen this happen, I will try to remember to have a little demo on Wednesday with this, but you can see this very clearly with when you fix one end of a string and you have a little pulse come in, it will come in upright like this, but it will actually leave upside down. Okay, if you have any questions about this, please send me an email. Otherwise, let's go on to the next topic, which is a standing wave. Okay, so let's consider, this is a little subtle, but let's consider two waves with same amplitude, same wavelength, and same period. Sounds pretty much the same. Oops, same period. The only difference is they move in opposite directions. Okay, so I have two waves. One is moving like this, and another one is moving like this. Now let's try to figure out what happens if I add them together, if I superimpose them together. So one looks like A times the sine of kx minus omega t, and the other one is A sine kx plus omega t. Remember, this one goes forward in x, travels that way. This guy travels backwards. Now if we add them together, what do we get? Now, in order to do the addition, we'll actually need a little, the derivation is not so crucial, but if you want to know how this is derived, you'll need this sign addition formula, that the sine of A plus B is this, okay, A is not this A, this is just a general A. Okay, let me just do a little aside. Sine of A plus B is the sine of A times the cosine of B plus the cosine of A sine of B. Okay, that's just a general formula. We'll use that to add these guys together. Okay, A, alright, sorry that this is the same A, that might be confusing. Kx minus omega t plus A sine of Kx plus omega t. Alright, now this is actually what I'm considering to be A, and this guy is what I'm considering to be B. Okay, so I can break this apart. Okay, it's not that hard. So let's do this. We'll get A times the sine of Kx, okay, and the cosine of omega t minus cosine of Kx. Don't worry about the derivation. It'll be done in just 1 more minute. Omega t, okay. And then we'll do the same thing for the plus sign. This minus sign will just go away. X cosine omega t, and it'll be plus cosine kx sine omega t. Alright, now the whole purpose of this is just to see what we get. These guys will cancel, plus sign and minus sign. And we'll end up with 2a times the sine kx omega cosine omega t. Alright? That might not look all that interesting to you, but notice that this is actually really quite different from these things. Notice that we have something that's a function of sine, we have a sine that's a function of just x multiplied by a cosine that's just a function of t. It's not a combination of x minus something with t inside the sine. It's a product of the sine of kx and a cosine of omega t. So what does that look like? That is actually what we call a standing wave. So what does this look like? Alright, it looks like this. So try to motivate this. Let's set t equals to 0. When t equals to 0, the cosine will be just 1. And let's just make life simple and just think about, we'll have the sine of kx, okay? So we'll have at t equals to 0, at t is equal to 0, we'll have a shape that looks like just the sine x. Okay, so what I'm plotting here is x. But then what will happen, let's suppose we choose t at some not 0, some slightly later time. Then the cosine will not be 1, but it'll be, let's say, some number slightly less than 1. Then the curve will look something like this at some later time t. And then you let time propagate a little further, and the cosine will be some number even smaller than the previous one. Okay, so then it will look something like this. Okay, then eventually it goes like that, and at some point the cosine omega t is 0 and it's flat, and then the cosine omega t will be negative at some point, and it'll do this. Okay, so as a function of time, it's sort of developing this way. This is what we call a standing wave. It's a string that's vibrating, where at each point there's like an envelope here, and the envelope looks like the sine wave, but each point goes up and down, and there's no sort of traveling motion anymore. There's none of this. The wave moves. It just looks like it goes up and down. Okay. Now this is actually what you'll see when you pluck a string on a guitar or a violin or piano. Well, it's hard to pluck a piano string, but when you pluck a stringed instrument or harp, something like that, if you look very carefully, and I'll have a demo on this where you can see this very clearly, you just see these shapes. So if it's very fast, you just see a big blur of the string just sort of vibrating like with these envelopes. You just see the envelope of the shape. All right, let me give you some terminology here. These places here where the string does not move, that's what's called, these things are called nodes. Each one is a node. No movement, nodes. Okay, nodes correspond with no movement. Now, they're halfway in between the nodes, this place here, okay? Or if you wanted to think about these points, it doesn't matter. It's just this whole location right here. Okay, these things are what are called maxima, or this is kind of a dumb name. They also go by the name antinode, which is the opposite of node. All right, so this is a node. These are nodes. These are antinodes. So either you can think of them as maxima because that's where you have a maximum vibration, or you call them antinodes because that's the opposite of the places where the wave doesn't move, the standing wave. Okay, so now let's consider where these nodes occur. So remember, this all came about because of this function here. Okay, we have this envelope, and then we have this sort of modulation of the wave, of the string, by cosine omega t. So the sine of kx is the envelope. So the nodes occur when sine kx is equal to 0. Okay? So let's probe that a little bit more. We'll think of the angle in terms of radians here. So when is the angle, the sine of an angle equal to 0 in radians? That's when the angle is 0, pi, 2 pi, 3 pi, like that. Okay? Let's not think about, let's just keep x positive, so let's just stay on the positive side. So the kx is equal to 0, pi, 2 pi, 3 pi, and so on. Okay? How about the antinodes? The antinodes are the maxima. The antinodes occur when sine of kx is equal to either 1 or minus 1. Okay? So that happens on the positive, let's just consider positive x, when kx is equal to pi over 2, so basically in between these points, pi over 2, 3 pi over 2, okay, 5 pi over 2, and so on. If this is not so obvious to you, just make a little plot of the sine function in terms of radians. So actually, let me just plot it as a function of theta, sine of theta. So here's pi, here's 2 pi. The sine function goes to 0 here, goes to 0 there. And right here is where it's equal to +1. And right here is where it is equal to -1. That's 3 pi over 2. Okay? And that's how I get these locations. All right, if you have any questions about this, please send me an email. Now, we will use this information to study the resonant modes, the modes of vibration for a string. And this has practical applications because this is basically what is a stringed instrument, how it will vibrate, the pitch you will hear on a guitar string. Okay, so let's analyze string of length L. So we'll call the string length L. So we have some string that has a length L, like this. Okay, so we can plot the string so that it's vibrating in what it's called the fundamental mode, and I'll try to show you here. So the string is going from there to there, and here's the envelope, okay, and the vibration will sort of be like that. It goes back and forth, like, it goes up and down that way. All right, this is what we call the fundamental mode. All right, the fundamental mode, we also call this it's also called the first harmonic. It's just the labeling scheme, okay? And we also say this is what we call the n equals 1 mode. N equals 1. It starts off at 1. Okay, and I will give you the wavelength of this vibration. Okay. In other words, what do I mean by wavelength? Well, this is a piece of a wave. It's actually just a portion of a wave. It turns out in order to get a full wave, I need another piece over here that keeps going on. But there's a wavelength associated with this, and I'll call it lambda 1 for the n equals 1 mode. This is just labeling schemes. It might look a little complicated, but it's not really that much. We're just going to go 1, 2, 3. We'll just label some modes here. Okay? And the formula is that lambda 1 is equal to 2L. All right. Now, I'll say some things, and I'll do the derivation. Once I do the derivation, you'll know how I came up with this lambda 1 equals to 2L. But I'll just put in a little helper statement here saying that half wavelength equals L. Okay, how do I see it's half a wavelength? Because this thing is half a sine wave. Okay, half a cycle of the sine wave. It's just one half of it. So half wavelength fits in the length L. So therefore, a full wavelength must be 2L. That's how that goes. Now, how about the next mode, the next simplest mode I can get? Well, I can have two of these things, like that. And this is the envelope that we'll get, vibrating like that. Okay, this length still remains L, but you see now this has a smaller wavelength. So this is what's called the n equals 2 mode, or the second harmonic. Okay. All right. For those of you who are musicians, if you were to hear this string, it would have the lowest pitch that would correspond with the lowest frequency. We'll talk about frequency in a second. And this guy will actually have twice its frequency. It would sound an octave higher. You don't need to know that, but for those of you who do some music, that's what will happen here. So n equals to 2, or the second harmonic. Lambda 2, that's the wavelength for this guy. Okay, so this is n equals 1, this is n equals to 2. Lambda 2 is equal to L. And the way I like to think of it is, in this case, I'd say I have 2 half wavelengths is equal to L. Okay, here's half a wavelength, just like we had here. This is half a wavelength. Here's another half a wavelength. We have 2 half wavelengths adding up to L, and so therefore that's 1 full wavelength is equal to L, and that's how I got lambda 2 is equal to L. Now let's do one last one. We can keep going forever, but let's just do one last one. So we have something like this. Okay. Oops. That's a little sloppy, but I think you get the picture. Okay. So here we have the n equals 3 mode. N equals to 3. N equals to 3. And in this case, we call it the third harmonic, you might expect. And the formula here is lambda 3 is equal to 2/3 L. So how the heck did I get that? Well, here's half a wavelength. Here's another half a wavelength. Here's another half a wavelength. So I have 3 half wavelengths. Is equal to L. So 3 halves lambda. So 3 halves lambda 3 is equal to L. And you solve for lambda 3, you get 2/3 L. So that's how I got this. Okay, now what's the general formula? The general formula is for the nth harmonic. Remember, we start off with the fundamental as being n equals to 1. The nth harmonic, the formula is lambda n is equal to 2L divided by m. Now, how do you derive that? Well, you just do what I said for each case here. The derivation is, let's take one of these half wavelength objects, and I actually like to call this a little football because everybody knows what I mean when I say that. It looks like an American football, okay? One of these things is a half a wavelength, but I'll call it a football because it looks like one. Okay, this football has length lambda over 2. Alright, so we're just counting footballs. There's 1 football here, there's 2 footballs here, there's 3 footballs here. Okay? So the pattern is for the nth harmonic, we have n so-called footballs. Okay? So what is the relation then? We have n footballs, each has a length of, now I'll put the little subscript in, lambda n over 2 for the nth harmonic. And that all together, I have a bunch of footballs lined up. Okay, I have a bunch of footballs lined up. I'll have n footballs that must equal, okay, that must equal L. So n of these things is equal to L. So then lambda n must be, let's multiply by 2, so I have 2L. And then divide by n, and that gives me the formula 2L over n. Okay? Alright, now we can go a little bit further with this. We can talk about things. First of all, let's review a little bit about the wave speed. So we're still talking about these waves on a string. So if the wave speed is v, then we know, since v is equal to the frequency times lambda, right? If you don't know that's the way I remember this is, once again, the wave speed has units of meters per second, frequency is inverse seconds, and lambda has units of meters. And so multiplying these things is, this is actually how I remember the formula, will give me something that has units of meters per second, which is the wave speed. Okay, so frequency times lambda is equal to the wave speed. Now, from this I can actually write down a formula for the frequency. It will be the wave speed divided by lambda. Okay, so now that I know a formula for the wavelength of the nth harmonic, I can get the frequency. Okay, what's the pitch? If we're listening to it, the frequency corresponds also with the pitch of the string. Okay, so we can say the frequency of the nth harmonic is, okay, so let's write down, let's keep our formulas here. So we have 2L over n was lambda n, and the frequency, so let's write the frequency, let's write it like this. Fn is a frequency for the nth harmonic, and that must be the wave speed divided by lambda n. Wave speed divided by lambda n. By the way, this wave speed is just a property of the tension and the wave, and as we said, whatever the tension is in the string, and what is the mass per unit length. That's what we did in the beginning of the lecture. Okay, so V is not changing with harmonic. It's just a property of the tension and the mass per unit length of the string. Okay, now we also had a formula for the wavelength for the nth harmonic. It was 2L over n. So let's plug that in, V, and then 2L over n here. Okay, so it's in the denominator, so I can put the n. It's in the denominator to the denominator, so it's the same as the numerator. And so I have nV over 2L. Okay, so this is actually the formula for the frequency of the nth harmonic. So it's like this. As you increase n, the frequency increases proportional to n. Okay? Alright, if you have a question about these strings, please send me an email. I should be able to read it and answer quite quickly. Let's do an example. Let's suppose a string has tension 5 newtons, length 0.50 meters, and mass 0.1 kilograms. Okay? And the question is, give a waveform basically the functional form for a standing wave. You know, one of these sine of kx times cosine omega t things with amplitude 0.020 meters, and in the second harmonic. Okay, that's kind of a tough question. Okay. Alright, that's actually testing quite a lot here. But it's a good kind of review problem that ties everything together. So you know the tension, you know the length, you know the mass. Give a waveform for a standing wave with amplitude 0.020 meters and in the second harmonic. Okay, what do we have to do? So we know the tension, it's 5 newtons. Now you may recall at the beginning of the lecture we had a way to get the speed of the wave from the tension and the mass per unit length. So it seems like we should try to get the mass per unit length, mu. So we have the mass is 0.10 kilograms. If I divide by the length, which is 0.50 meters, that will give me 0.20 kilograms per meter. Okay, now what was that formula for the wave speed? We know, okay, let's see. The wave speed is V is equal to the square root of the tension divided by the mass per unit length. Okay? Alright. Now, so I just need to plug in the tension is 5 newtons divided by 0.20 kilograms per meter. Okay, and that comes out to 5.0 meters per second. So that's the wave speed. Okay, but we're still not close to being done with this. So what else do they tell us? They tell us second harmonic. So let's look at the second harmonic. Okay, so let's try to use what we just learned. We said that the wavelength for the nth harmonic is 2L over n. So let's do it for the second harmonic. So it's 2L divided by n, which is 2, so that's equal to L. And we know what L is, that's 0.5 meters. Okay, how about the frequency? The frequency is NV over 2L, where we stick n equals to 2. So we'll have 2V over 2L, which is V over L. And so what did we get for the wave speed? We got 5 meters per second for the wave speed. Okay, so 5 meters per second divided by the length, which is 0.5 meters, and so that's 10 inverse seconds, or 10 hertz. Okay. All right, now what I need is from this I can actually get the waveform, right? So y is equal to, it has this form, a sine of kx times cosine of omega t. Right. Okay, but I need k and I need omega, right? One way to do that is just plug in the formulas for k, that's 2 pi divided by the wavelength, okay? And cosine is, the omega is 2 pi over the period, right? In fact, we did that on Friday. Now we'll just plug in, so, well, we didn't actually get the period yet, so let's do the period. The period is 1 over the frequency, okay? 1 over the frequency, so we have 1 over 10 inverse seconds, and that's 0.1 seconds. Okay, so now we're ready to go. We were told, now we use the very last piece of information, that the amplitude, sorry, where was that? The amplitude has, yeah, the amplitude is 0.020 meters. So we just plug that in, leave that there. Then we have the sine of 2 pi divided by whatever the wavelength was. You got it was 0.50 meters, okay, times x. And then we have the cosine of 2 pi divided by the period, which is 0.10 seconds times t. Alright, so now we're pretty much close to killing this very long problem. So the waveform is 0.020 meters times the sine of, now we just plug in 6.28 for 2 pi divided by 0.5 gives you 12.6 inverse meters times x. Okay, and the cosine of 6.28 for 2 pi divided by 0.1 gives me 62.8 inverse seconds times t. Okay, that's what it looks like. That's what the actual waveform will look like. Okay. Now, I realize there is actually a little bit of ambiguity as to what if you want to put a little phase angle here or something like that. But this is the simple waveform as we did it for the string previously. Okay, now so if you have a question on this, please do send me an email. The last thing we'll talk about is what happens when a wave passes from one material or one medium to another. Okay, so I'll use the term medium because it could be, for example, a string. In fact, you have this in your homework due on Tuesday. You have two strings, one made from a light string, one made from a more heavy string. Okay, and so they're coupled together, and they're asking what happens when the wave from one string passes through to the other string. Okay, so the medium will be sort of a general term. So consider a wave in medium 1 going towards the boundary with medium 2 material, or whatever string, perhaps either a material or a string. Okay, so we have, this is the boundary. Alright, and here's medium 1, and here's medium 2. Okay, so we have some wave here coming in. Okay, that's the initial situation. Alright, now what will happen is some of this wave will actually go through. So we'll have motion going this way. Okay, that's what's called the transmitted wave. Just like light going from one material to another. That's we'll talk about. You will talk about light though in PY205, not in this class, because it's a bit more complicated. But that's an example of a wave that can be transmitted from one material to another that you're probably quite familiar with. But there's also some of this wave that will actually bounce off the boundary. Okay, it will actually go this way. Okay, so this is the final situation, if it's not clear. And this is what's called the reflected wave. So the reflected. So this is the initial picture, this is the final. Okay, so we have transmitted wave and a reflected wave. Okay, this is medium 1, this is medium 2, if it wasn't clear. Okay, what else can I say about this? Now, if we have two materials, so think about a light string and a heavy string, and if I have a vibration that's transmitted from one to the other, it's not true that the wavelength will be the same in one material as in the other, and it's definitely not true that the wave speed will be the same, because they're different. You know, the wave speed will be determined by other things. Okay, but what is true is that whatever the oscillation is at the boundary, they'll be going up and down at the same time because they're connected. So they actually have to vibrate with the same frequency. That's the key in this sort of transmitted and reflected wave. So the frequency will be the same. Will be the same in medium 1 and medium 2. Okay? So what I mean by the same is all these things, they all have the same frequencies. The initial wave, the final wave reflected, as well as the final wave transmitted, all these guys will have the same frequency. Okay? So let's sort of write this down. So here I have the initial wave coming in. Okay, here's the initial wave coming in, medium 1, medium 2. Okay, so we have frequency F, and suppose I have some wave speed for 1. I'm not going to write the words, I did it in my notes, but F is for frequency, V is for wave speed, wavelength is for lambda is for wavelength. Okay, and then for the final case, what do we have? We have some wave going the other way, like this. And I'm just going to talk about the speed, not the velocity, so don't worry about any minus signs here. So the frequency will remain the same, it's F. Okay, the wave speed will remain V1. And the wavelength will remain lambda 1. It's just going in the opposite direction. So this is medium 1. And now what happens in medium 2, we'll have a little bit of a transmitted wave. Okay? And it'll be going this way. But in this case, the frequency actually will remain exactly the same. In both media, they go up and down here the same. That's why the frequency is the same. but the wave speed will be different because it's a different medium. They'll have some natural speed for the waves in this medium, v2. And the wavelength will in general be different as well. Okay. Now we can try to solve for these things. So the frequency will remain the same. That's very simple. The wave speed you can calculate just from the property of the material. But you might not want to know. You might want to know what is the relationship between lambda 2 and lambda 1. Okay. So let's do that. It's a pretty quick calculation. So the wavelength. All right. Okay. So what do I know? I know the wavelength times the frequency is my wave speed. Frequency times wavelength gives wave speed. Okay? F is the same for all of them, so I don't need a F2 here, just F. F times lambda 2 is equal to V2. Okay. Alright, so now what I can do is I can say, well, I can write an expression for lambda 2. Lambda 2 is equal to V2 over F. Okay. Very good. Now, let's try to get some information about F in a slightly different way. Let's do the same thing for lambda 1, okay, medium 1. I know that the frequency times lambda 1 is the wave speed in medium 1. Okay, so that means I can write an expression for F that's going to be V1 divided by lambda 1. Alright, good. So now I'm just going to shove this guy in here. And then I'll get an expression for lambda 2. So I'll have lambda 2 is equal to V2 divided by this thing, V1 over lambda 1. Or I can write this in a bit simpler way. Lambda 2 is equal to lambda 1 times, okay, lambda 1 came upstairs because it was in the denominator of the denominator, times V2 over V1. Okay? That's what will happen to the wavelength. So the frequency will remain the same on both sides, but the wavelength will change. It is just multiplied by a factor of the ratio of the wave speeds. Okay, so that's the end of the lecture. If you have some questions, please send me an email, and I should be able to respond quite quickly. So I'll see you guys in class on Wednesday.